and Interchange. And once again, I am Carla, Editor-in-Chief of Tengri Energy. And we have the pleasure today of hosting Steve Krase of Hephae Energy Technology, a company that is, I would say, at the forefront of developing high-temperature tools and electronics and sensors for geothermal drilling. Steve is a geoscientist and drilling technology innovator with 45 years of industry experience. He co-founded Navigate Energy Services and guided it through its successful sale to NABCORS in 2012. He has multiple patents and a career devoted to advancing drilling technologies, and Steve remains the driving force in the energy transition. As Hephae's co-founder and CEO, he remains at the forefront of developing high-temperature technologies that are accelerating the geothermal industry. Now, I'm personally very interested in hearing all about the progress being made in high-temperature sensors and electronics, and I think this is going to be a key component of trying to unlock higher temperature geothermal resources, which in turn can produce power and heat at much higher efficiencies. So I'd like to introduce Steve. For everyone in the audience, you can send in your questions. There should be a questions tab somewhere in the webinar interface. So just type in your questions at any point, and then we'll get to those after the presentation. And with that, Steve, the floor is yours.
Great, thank you for the introduction and the opportunity to present what's going on here. Did I lose you guys?
Sorry, we don't see the presentation.
Like something changed here? Apologies, guys. I don't know what's going on. How's that?
Okay, yeah, you're good.
All right, sorry about that. I'm not sure what happened. Anyway, so yeah, the Hephae is focused on developing high temperature electronics and robotics to enable what we're calling next generation geothermal energy. So the first thing I'm going to do is talk about why we're doing what we're doing. And you know, I started my career back in actually my career started in 1980, working on petrophysics, formation evaluation. 1984, I joined a company called Teleco, which was the first commercial measurement well drilling system. And back in the 80s, we used to send our MWD systems up to the geysers to drill, to provide survey services for, right now it's Calpine. Back then, I think it might have been Unical that we were providing that service for. But that was all targeted on what we're calling hydrothermal, conventional geothermal energy development. And John Clegg and I formed Hephae. When John Clegg and I formed Hephae 5 years ago, we actually before we formed Hephae, we actually thought we knew a lot about geothermal energy, but we were really kind of stuck in the past and focused on you know, what's going on in the geysers in the Indonesia and Iceland, where you're targeting pockets of steam or hot water, and you drill typically a vertical well or a slightly deviated well. The directional drilling part of it is not that complicated, and you try to tap into what I call these magic pockets of steam that you can find in various places around the world, primarily around the Ring of Fire. And it's great if you can find it, because then you could just take that steam. You don't have to burn natural gas or coal or have a nuclear reactor to create the steam. You just take the steam, spin a turbine, generates electricity, and provides it to the grid. And then any water that you have left over, you inject it back into the formation. The picture on the right is actually from Lauderello, Italy, and I think that's back in the 40s. They were doing geothermal energy development in Italy. That's the first use of it for electricity generation. But what we're talking about today, the promise has always been, is there any way that we can use the heat that's in the earth and not rely on finding these magic pockets of steam or water to create electricity? And so we've been trying for a long time, and I say we, the industry, trying for a long time to figure out a way to take advantage of this heat. What we're calling next generation geothermal has the promise of generating electricity anywhere on the earth by circulating working fluid through what used to be called hot dry rock. Now it's just all called next generation geothermal. And so today what we see is three major types of approaches to this. There's more, but these are the three that we're looking at today that seem to show the most promise. The one on the left with the multiple fingers, looks like fingers. That's actually Ever has got a system like that. They just installed this their first system in Germany, and what it is a series of directionally drilled wells that are connected at the toe, and then you create a loop, pump cold water down the blue leg there, and then hot water or steam comes up the red leg, and we use that for, you can then take that, flash that into steam to spin it and spin a turbine and generate electricity. But the other thing you can do is you can use that hot water for district heating. And in Europe, a lot of the cities are set up for, they have a district heating network, so you can just take the hot water and pump it into the heating grid, not the utility electric grid. The other closed loop system that we see out there, and a company called XGS is doing this, and that is they've got one well that's cased, and you've got a stinger pipe down the middle, and the goal here is to put this into the hottest rock that you can get it into, and then you pump cold fluid down around the annulus, and then hot water or steam comes up through the center stinger pipe. It's like a coaxial system, and then you generate electricity from that steam that's coming out, or you, of course, you can also use that for district heating. And then the last one, and the one that is probably the most in the news today is enhanced geothermal systems, EGS, and this is a representative of a company called Fervo, which most of you have probably heard of, and they're taking a different approach, leveraging off of what we've learned in unconventional oil and gas, and drilling two horizontal wells, or a series of horizontal wells, into hot dry rock, fracturing between the two, and then pumping cold water down into one well. It percolates up through the fractured rock, and then produces supercritical or hot water steam through the other well. So you've got an injector and a producer, and create a series of these. So the difference here between hydrothermal and or the conventional geothermal here is that we're not relying on finding water or steam. We can do this any place on the planet. It's just a matter of how hot a rock can you access. Now, there's two things that all these systems have in common. One of them is hotter is better, and I'll talk about that in a minute. The other one is the surveying requirements are pretty much the same as we've seen in oil and gas over the years. And in the case of Fervo and Ever, the one on the left and the one on the far right, the wellbore placement is extremely critical. And so one of the things that we see as we go around and we talk to investors and people that are not familiar with the drilling industry, the question is always, why do you need electronics for downhole, right? There's just a lack of understanding of what's required to actually drill these wells and put them in the right place. So what we see is that these unconventional wells, these next generation geothermal wells, they need exactly the same tools that we've been using in unconventional oil and gas. This is an example of a system that you would typically see on a long extended lateral, say in the Permian Basin. An MWD system combined with a rotary steerable system. In most cases, these are two separate systems. What we decided was that, especially considering the importance of high temperature electronics, it makes a lot of sense to just have one set of electronics, one set of sensors, and that can control the steering head and also provide the survey data that you need to actually steer the well. The system that we've concepted, that's pictured here, is top mount pulsar, positive pulsar on the top right, turbine generator that uses the mud flow coming through the center of the tool to generate electricity and power for the system, and then high temp electronics and sensors down below that, and then the steering head that is below it. Right now we're testing the MWD portion of this, and we hope to be in the ground with the complete system with the steering head sometime in 2027. The existing system is rated to 210 degrees Celsius circulating temperature with a 230 C survival, but we have plans to push this to 300 degrees Celsius. And I'll talk about that in a minute. So why are we doing this? When you look at the electricity demand that we're looking at by 2050, whether it's 50 or 70,000 terawatts, it's a big number, and it's increasing considerably. And that's why we're seeing this significant amount of investment that's projected here to continue to increase. But look at on the right, you can see the investment that we've seen just in the last 7 years. It's been incredible. A lot of it has to do with Fervo's success in Utah with Cape Station, and they are. Rumor has it there's an IPO coming out here just after their 462 million Series E raise. We've just seen the hot rock bill introduced into the U.S. Congress, and Mazama is another company that's drilling EGS wells. Just announced the world's hottest EGS system. They're going to be targeting 370 C rock on the Newberry volcano starting later this year. So we think, and so does a few other folks in the industry. Here you've got a quote from our friend Ross Loudon over at Schlumberger, or SLB, that we think the next generation geothermal has bigger future potential than oil and gas. What that means is we believe that this is actually, there could be as many rigs drilling geothermal wells in the United States and around the world as there are oil and gas wells. This is independent from Merritt Brommer from IEA, and her projection is 20,000 wells, total of 63 gigawatts by 2050. And yeah, this could actually be conservative in our opinion. Okay, so let's talk about temperature. So why hotter? In oil and gas, we most of the reservoirs that we attack, with some exception, like the Gulf of Thailand, and most of our reservoirs are well below 200 degrees Celsius, and so we've not really had the demand for higher temperature electronics. But in the case of next generation geothermal, where you're targeting hot dry rock, I mentioned it earlier, hotter is better. And the graph on the right shows you the relationship between LCOE, which is the levelized cost of energy or electricity or cost per kilowatt hour, versus the reservoir temperature. Now I say reservoir temperature, it's just hot dry rock. So you can see on the left, I've got the reduction of LCOE versus temperature. And if you look at just in the top left corner there, 200 degrees Celsius, which is roughly where Fervo is drilling today. If we can start to drill into 250, 270 degrees Celsius rock, we can reduce the cost of electricity generated by geothermal by 50%. The goal here is to get to the point where we're competitive with natural gas, and we believe that we can do that by combining hotter rock with longer lateral length and bigger hole size. The challenge here is the current projects rely on existing oil and gas technology, and that limits the temperature that we can access. We know how to drill these wells. The challenge is we just don't have the technology to get into the super hot rock, supercritical rock up to 400 degrees Celsius. So a little bit about the oil and gas capability. So when I first started in '78, mil-spec electronics were 85 degrees Celsius. And that's what we used. We inched our way up to 100 and 125 Celsius. And then finally, we had 175 C Celsius tools in '96, thanks to our friends at Sperry Sun. And then we really haven't moved very much since then. There are some systems out there that are 185 C, 195 C, 200 C systems, but they're essentially 175 C systems that have been tweaked. And basically, in 20 years, the industry have gained about 90 C of capability, and it gives us the ability to drill the majority of the oil and gas reservoirs. But we've pretty much been stalled since 2000. Some things that we do today to enable the use of standard MWD systems are coated drill pipe, insulated drill pipe, and mud chillers on the surface that can keep the drilling fluid cool. The chillers reduce the temperature of the fluid that's introduced, and then the coated drill pipe or the insulated drill pipe can keep it colder for longer. But there's a growing recognition that these technologies just are not a complete solution. One of the other things that you hear a lot when you talk about geothermal wells is you hear this story that it's very expensive to drill these wells. Well, you have to be careful when you hear that, because a lot of the times people are talking about older conventional geothermal wells that were drilled without a top drive, without a PDC bit, and we believe that the state of this next generation geothermal industry right now is roughly where unconventional oil and gas was in 2009. So we expect to see the same improvements in drilling rate and reduction in drilling costs that we've seen in unconventional oil and gas as we get a little bit further into this development. And just as an example, when I started my career, drilling granite was just something you didn't do. In fact, you didn't even want to drill shale. It was not unusual to drill 3 to 5 foot an hour if you hit a shale bed offshore. Now we're drilling shale in excess of 300 foot an hour, and we're drilling granite 100, 200 foot an hour. And so we anticipate that improvements in drilling technology here, as we learn more about drilling these hot dry rocks, which are a lot of times are igneous basement rocks, we're just going to keep getting better at it. Here's that example of the evolution of directional drilling in the United States, the cost. And from just in 20 years, the percentage of wells in the U.S., first of all, it moved from 12% to 85%. And as we started to drill these wells and get more experience, we increased the performance by more than 3x. And we expect the same thing, the same improvement in next generation geothermal. So talk a little bit about some of the mitigation techniques. One of them is insulated drill pipe. There's several different companies out there that use this, and we see this in application in some of these applications, where especially when you're starting to target 350 degrees Celsius rock. And to be, just to put it in perspective, right now, the Haynesville is considered, the hottest area that we're drilling for oil and gas, at least in the United States, where, we've got reservoir temperatures in the 200 degrees Celsius kind of range, plus or minus. The stuff that we're targeting now, that Mazama is targeting in the Newberry volcano, is 150 degrees Celsius higher than the Haynesville. And so when you're in that environment, you've got to start to bring in some other things, but we don't think it's a complete solution. So this is essentially it's insulated drill pipe. It's essentially a flask that is created in drill pipe, and keeps the fluid cool as you pump it down hole. Okay. The other thing we're seeing is a coating. This is very popular. That we're seeing it a lot in the Haynesville, and it's more a little bit more cost effective than the insulated drill pipe. But these coatings are being used just about every place that's drilling any kind of wells above 175 degrees Celsius circulating temperatures. The other thing is mud chillers, and on some of these installations, we're seeing upwards of 2 to 3 mud chillers on location that are used to chill the mud as it comes out of the hole. It goes through these chillers, and then it reduces the temperature, and then pump back down the hole again. Now the challenge is that's great when we're circulating, and we've cooled the mud and we've circulating all the time. But as you guys know, sometimes we have to come out of the hole, whether it's for a bit trip or a motor failure or an MWD failure, and then the wellbore fluid heats up again rather quickly, and as evidenced by the graph on the left. And so what we see these companies doing is they have to do what's called staging. So you've come out of the hole, you're in 250 degrees Celsius rock, 300 degrees Celsius rock. You've successfully kept it down below 200 degrees Celsius. You come out of the hole. Now you've been out of the hole for 24 hours. The drilling fluid that's left in the hole has increased in temperature, starting to approach the formation temperature. And you cannot run straight back to bottom because the limitations on primarily on the electronics. So what you have to do is you have to stop, you have to circulate. It's called staging, cool down the mud, go a little deeper, stop, cool down the mud until you can get it down to the point where the MWD equipment can handle it. This is very expensive, and this is one of the reasons why coated drill pipe chillers and coatings, coated drill pipe, insulated drill pipe, and chillers aren't the complete answer. You still have to be able to handle getting back to bottom and run it back to bottom without having to stage. So it's a huge savings to operators if we can eliminate this staging. So let's look at why we need high temperature electronics. And this is actually from hundreds of wells in the Haynesville. One of the Haynesville operators was kind enough to give us access to all of their data. And so what you see here is the probability of failure versus temperature. And the first bin, 120 Celsius, all the way up to greater than 200 Celsius. And so the blue is MWD failure rate, and the orange is mud motor failure rate. And if you focus in on now these, to keep in mind, these systems are all rated to 175 degrees Celsius. But if you look at the first two bars, you see 120, from going from 120 Celsius to the 120 to 140 C Celsius range, you see a tripling of failure on MWD rates. And this is what we would expect. And there's a general rule that for every 10 degrees of temperature, you get a reduction in reliability by 50%. And this kind of supports that. Now, the failure rate for MWD drops off after 140 Celsius only because the mud motor performance historically in the Haynesville has been significantly worse than the MWD performance. So what happens is you come out of the hole and you don't have the MWD system is not exposed to the temperature. The motor failures are actually masking the lousy reliability that you see at MWD at higher temperatures. Okay, so why is that? This is existing high temperature electronics. This is actually from a paper that was written by Weatherford in the public domain, and picture of their high temperature electronics. And you know, Weatherford and Halliburton both have developed high temperature electronics specifically for high temperature offshore work, Gulf of Thailand, the way that most electronics today, well, actually all electronics that I've seen in downhole tools pretty much look like this. And they're long and skinny because historically what we do is we have to go into standard drill collars. And but either way, we're going into drill collars, and it has to be long and skinny to fit into the pressure barrel. And then what we do is we'll take these long skinny boards and we will package them in, I don't have that slide. Okay, let me go back. Sorry, guys. And then what we will do is we will package this in silicone, or what we used to call it Baker Hughes, we used to call it Pookie, and just cover this up to protect it from shock and vibration. And that's great for shock and vibration, but not great for temperature dissipation. So this, again, the historical approach is we screen electronics, and we'll put the high temperature rated components on a printed circuit board, and then we will screen them. We'll figure out which boards actually will work, and that's typically historically how we've developed high temperature equipment. We use screening of components and systems to get to the highest temperature we can, but we don't believe that can get us to reliably above 200 Celsius. Again, we think that this has to go to 300 Celsius. So one of the things I've learned through my career is that if you want a step change in performance, you've got to start with a blank sheet of paper, and that's the approach we've taken. I'll show you that in a minute. But so the historical approach has been screening. You've also can do ASICs or multi-chip modules. The challenge with those is they're very expensive and very high non-recurrent engineering if you have to make changes to it. Very expensive systems. They're uneconomic for low volume, high temperature measure while drilling rotary steerable tools. And we believe that there is a better approach in the short term by using discrete components selected for temperature resistance and protecting them from temperature. And there's a more economical way of building. It's a more economical way of building small quantities of tools. So when we look at this, we look at three key requirements. And first of all, you've got to protect the assembly from the external borehole temperature. But the way that we see it is the mud chillers, the coated drill pipe, the insulated drill pipe does a pretty good job of keeping the drilling fluid cooler than the surrounding rock, at least while you're circulating. So we have that. Secondly, you've got to protect the components from themselves and quickly move the heat that the components generate internally. And John, my partner, John Clegg, likes to use the example analogy of your cell phone. If you stay in your cell phone for very long, it heats up, and the same thing goes for downhole electronics. We've got the electronics will heat themselves up, and we've got to move that heat away quickly to someplace that it's not going to do any harm. We can't destroy the heat, but we can move it, and that's our focus. So instead of long skinny boards, what we decided was that the best way to do this was a circular board. And you'll see the picture on the right is actually our processor on one of our boards. And the reason we've done this is this from the center of that board to the from the center of the component to the outside of the board is a very short distance. And it's essentially, and we have, it operates sort of the reverse of a choke. The heat wants to move out radially from the center of that component. We've got special material that's embedded inside that the actual circuit board itself that prioritizes heat dissipation. So we're moving heat very rapidly out to the tabs on the side of those boards, and then we have a stack of them. You can see the tabs are actually aluminum. They're actually aluminum guides that will then take the heat and then move it out to the pressure barrel and down to a bulkhead that we have at the bottom of the system. So heat comes off the center of the components very quickly out to these outer ring, and then it moves the heat out into the drilling fluid. So with the drilling fluid going past, we've got a continuous heat sink that we take advantage of. And so this is a little thermal modeling of how that works. And so what we've seen with standard electronics is that you can get up to a 40 degrees Celsius increase in the die itself if you don't move the heat. If you just leave it insulated in silicone or whatever you're wrapping your electronics in, you will get a 40 degrees Celsius increase over the circulating temperature of the mud. And what we take our circular board and we model it, we're able to keep the temperature within 2 degrees of the circulating fluid. So what we feel like to remain cost effective, the cooling must be used selectively. You don't want to make the whole assembly work natively at the maximum rated temperature. That is, if I go back one of the nice things about this is we can if I have a set of electronics that works up to 300 degrees Celsius, I don't have to worry about it. If I have a set of electronics or a sensor or components that only go to 210 or 250, I can isolate those and treat those differently with some other cooling method. So you don't want to cool the whole assembly. With the system that we have, we don't have to cool the whole assembly. If we want to cool something, we can put it into a separate chamber and keep it in its happy place. And the design is optimized to allow for modular cooling. We have done Hall testing on the system. Everything has been tested above 230 Celsius, 30 Gs of vibration, and everything is working above 210 Celsius and survival up to 230 Celsius. We think that the shock and vibration in these deep geothermal wells, considering the high coefficient of friction in the granite, that we're going to be seeing a lot higher shock and vibration conditions than we see in oil and gas. And we've tested everything at a 50% increase of shock and vibration of what we would normally do with oil and gas systems, and using highly accelerated live testing to find the weak links, and then HASS screening for manufacturing and production. I'll show you guys a little video. This is from, we did our testing at Dynaqual, which is here in Houston, and a great facility, independent lab that's been around for over 20 years. And they do a lot of testing for the major service companies and also for NASA. I'm just going to show a quick video here that my partner John Clegg put together.
Hi, John here from Hephae. Our mission is to enable geothermal energy at scale. And to do that, the industry needs to drill wells which are deeper and hotter and in harder formations than the oil and gas industry ever saw. Hephae's part in that is to make sure that our equipment survives and thrives in those difficult environments. And therefore, before we even think about putting a tool down hole, we're going to subject our technology to the harshest laboratory test conditions that drilling equipment has ever seen. During the course of last year, we did a lot of oven testing of all of our printed circuit boards. We subjected them to high temperatures under full operating conditions to see where they would survive and where they would operate. And I'm pleased to tell you that everything passed. All of our boards survive at least at temperatures of 230 degrees Celsius, and they all operate successfully for extended periods at temperatures significantly higher than the 210 degrees Celsius operating temperature that we've set ourselves for our first product, Pandora 210. Then we take the boards and we put them in a vibration chamber. Here, we're taking a board or an assembly and we're subjecting it simultaneously to high levels of vibration and very high temperatures. Typically, in the oil and gas industry, boards are tested to about 20 G of continuous vibration. But we're designing these tools for geothermal wells. They're going to be deeper, they're going to be in harder formations, there's going to be more friction, there's going to be more vibration. So we're not testing at 20 G, we're testing at 30 G. We're testing 50% higher than typically oil and gas tools would have been tested. And we're testing at 230 degrees Celsius, which is very, very high compared with the typical temperatures that oil and gas tools are rated to. Shock is where we subject the unit under test, the board or the assembly, to very high levels of acceleration. So we take the board in its assembly, we lift it up, and we drop it. Bang. And then we lift it up, bang, we drop it again, and again, and again, many times. And the great news is, all the boards we've tested so far like this, through this punishing regime, they've all passed. No problems at all. Successfully concluding these tests gives us the confidence that we will work first time when we go into a real-world drilling environment. It's not sci-fi, but it is rocket science.
All right, thank you guys for that. Let me see if I can move this forward now that I've done that. Okay. All right, so I'm going to get a couple slides here to wrap up. So we know shock and vibration is going to be tough in these deep geothermal wells. High coefficient of friction, this is going to be a challenge, absolutely no doubt about it. We've done the very most we can do from a highly accelerated live testing standpoint, and we're screening everything also with temperature and thermal cycling simultaneous with acceleration. And one of the things that we have seen is we're up against, at least locally, we're up against limits on the combined temperatures and shock and vibration that we need to see. So right now we're able to test at 230 Celsius, but at the end of the day, we're trying to get systems to work at 300 Celsius. So we need to be testing well above 300 degrees Celsius, and finding those chambers, at least locally, has been a bit of a challenge. the three key requirements for these electronics are protecting the assembly from the borehole temperature, from actually the formation temperature, and then protecting the components from themselves by moving the heat and putting the heat someplace where it's not going to do any harm, which is into the drilling fluid. And we've demonstrated that this stack of circular boards can meet these conflicting requirements. And looks like everything is working well above 200 degrees Celsius. We think we can get up to 220, 230 Celsius with the existing packaging scheme that we have. In order to go to 300 and above, we're going to have to bring in some other things, and we're working with. We're just about to get a Space Act agreement signed here, which will give us access to some of the technology that's being used on the Venus rover. That's going to be going to 500 Celsius. So we have a roadmap to get to 300 degrees Celsius by 2030. So that's me, guys. Thank you very much for the time, and I appreciate it. And I think we have questions. I'm happy to answer them.
All right. Thank you, Steve. Thank you for that presentation, that update on the technology that you're working on. It's all very interesting. We have a handful of questions now being sent in by the audience. For everyone else, please feel free to send in your questions. I'm not sure if my audio is still off, but we'll manage, I suppose. Okay, then. You mentioned there was a graph you showed earlier that showed the failure of MWD and mud motors at different temperatures, and I think something that kind of stood out was that mud motors also failed at temperatures of 160, 180. So is this something that you also have to work on, or is this an issue that has already been resolved since then?
No, we're not tackling that. The mud motor power section providers are working hard at that, I believe. But that is something that we're leaving that for somebody else to worry about. Put it that way. Yeah. No, we're not working on that. But that's definitely getting these elastomers to survive in these temperatures is a challenge. You know, there are some folks talking about using turbine instead of to get rid of the elastomers. So I know there's some efforts underway to do that, but that's definitely something that, and I would say it's also one of the reasons why with the rotary steerable, interest in rotary steerable, I know right now in the United States, most of the rotary steerable runs are motor assisted. So with the rotary steerable, theoretically you can rotate just from surface, which obviously has its challenges, but that's one of the interesting things that we've seen from the interest from operators for rotary steerables, perhaps getting rid of the motor.
Yeah, okay. I think that's also going to be an interesting topic to follow up on.
Yeah.
A few questions here specifically on the tool. An issue on maintaining telemetry in loss zones. So does the tool use mud pulse telemetry, or does it use EM transmission?
Mud pulse telemetry, we thought about EM, but our concern is being able to transmit the EM signal through what we think is probably going to be granite in most cases. And we know there's other ways to do that by downhole antennas in neighboring wells. But for the projects that we're looking at right now, where they're drilling on water-based mud, low mud weights, telemetry has not been an issue. Mud pulse telemetry has not been an issue. The other thing is we're not so far, since you're drilling massive granite or igneous rock, basement rock, we're not doing any geosteering. So data rate, we're transmitting ink as temperature, gamma ray, and but that's it. There's no at the moment there's no high speed telemetry requirements. So mud pulse telemetry is working great.
And I suppose if you're targeting, say, EGS projects, and you don't really expect large loss zones.
Large
loss zones, sure.
No, we do see high. We have seen high. If you're one of the things about granite and basement rock is it's usually fractured. So we do have to. When I say we, operators have to address that. So yeah, no, lost circulation is for sure an issue in these wells, or can be. Not all wells, but they can be if you encounter a fracture zone. That's the nice thing about the closed loop system is, EGS. Well, I take that back. That's nothing to do with it. The nice thing about AGS systems is you don't have to worry about the geology as much, right? Once you get it drilled, you get the rocks behind casing, you don't have to worry about it. With EGS, you've got some other issues. But yeah, no, I misspoke. Yeah.
Okay, then there's a question here that mentions some of the earlier work done on trying to drill very high temperature wells. So I mean, there's been some work done in Italy, there's been some work done in Iceland, in Japan, in the US. Do you have any insights on if there were like specific failures of electronics or MWT tools during these operations?
Yeah, well, most of those well, again, there's a lot of different operations out there, so I can speak to the hydrothermal work that's being done in areas like the geysers and Indonesia, places like that. And so those wells are not horizontal; they're vertical wells. You can get by without taking a lot of surveys. And in the case of a lot of the wells on the West Coast, you'll get your directional work done up shallow, even in Southeast Asia. You'll get your directional work done shallow where it's not hot, and then you get yourself positioned above the reservoir, and then you put together a bottom hole assembly that's going to try to stay straight, and then or a tangent or whatever your projection is, and you just try to drop into that magic pocket of steam. So the directional drilling requirements in the high temperature is actually not that critical. And if you need a survey, you have to drop a wireline survey that's flasked, and you can get a survey. Obviously that's very expensive.
Okay, then. So you're trying to solve perhaps more complex problems than say some of these higher temperature wells that have been drilled in the past.
If you're drilling a vertical well at high temperature, you can get that done. You may not know where the bottom hole location is because you're not getting great surveys. But in the case of all of these next generation geothermal wells, you have to put these wells. Wellbore placement is critical, especially in the case of what Ever's doing, and in the case of what Fervo's doing. XGS, the coaxial system, you have a little bit of leeway, even if you're drilling a slightly deviated well or tangent, which I think is what they're planning. Your survey requirements are not that critical. But yeah, no, there are currently no systems in the industry that are operating above 200 degrees Celsius circulating temperature.
Okay, then how does your tool fit into the existing drilling supply chain? Like, is it something that can be used seamlessly with existing borehole assemblies?
Yeah, that's a good question. So the way we've designed this, and the way that we're envisioning at least early operations here, there's no reason to run this system shallow. If you're getting good reliability out of the MWD system, the way that we see this is it will continue to use the existing MWD systems until it gets to be too hot, and then we'll pick up a Hephae tool. And the way we've designed the system, we're using the MWD transmission standard, which is called MRE encoding. And the way it would go and the way we're planning to operate now is we would send our tool out, and once it gets in the ground, it will look exactly like the tool that the low temperature tool that was in there. We're going to use, the plan is to use existing decoders. So we will set up the tool. The telemetry will be exactly the same as the tool came out of the ground, or we can modify it, but it will work with existing surface systems. And the intention is to leverage off of the existing footprint that's there. We don't want to interfere with ongoing operations. So this should be invisible to the operator.
Okay, then something more specific again. What is the planned OD and length of the electronic stack?
Say that one more time.
What is the planned outer diameter and length of the electronic stack?
What is the length of the electronic stack?
Yeah. Yeah.
Oh, that's
Yeah.
a good question. We've got right now. We have two stacks. We have a stack for the pulsar controller, and then we've got a stack for the sensors and processor. Both stacks, they're about 9 inches, 9 inches to 12 inches long. So we've got about 2 foot of stack.
Okay, then it's a 2 foot stack.
We have,
Are you
yeah,
are you
go ahead.
working on an RSS tool?
We are, we are, we prefer not to. What the way that way we envision this and what we'd like to do is we're set up. We have a brushless DC motor at the top that controls the valve, the pulsar, and we've got one at the bottom that would control a steering head, a push the bit style steering head. So we're in discussions with most of the companies that have those types of systems, and the way we see it is we could just add the steering head to this to our system. However, we've just kicked off our own steering head project. But we think that if we can, the thing about this is that this industry, we need to access hotter rock, and we need to start drilling 3-mile long laterals. And we believe that the best way to do that is with the integrated system that we showed, and it's got a combined rotary steerable that's going to be rated above 210 degrees Celsius. And we think if we can collaborate, and it's not just us that need to collaborate, everybody in this industry, everybody has been collaborating, because we got to address this now. And the way that we're going to tackle this is if we can get in the ground and start drilling 3-mile long laterals at 375 C, 400 degrees Celsius rock. And if we all collaborate together, we can get this done. Like next year, we could be drilling high temperature 3-mile long laterals next year. And yeah, I realize the market is small today, but we believe that this is going to be bigger than oil and gas. So that was a long-winded answer. But yeah, no, we're not. We just kicked off a rotary steerable project, but we prefer to just to collaborate with somebody on that steering head, where we provide the electronics and somebody provides the steering head.
Yeah, I mean, as you mentioned with the mud motor, it's you kind of have to give the problem to someone else.
Yeah. I think our plate's full with the electronics, and we'll stick with that.
Okay, then a note on collaboration. You mentioned earlier that you're working with this group that is also developing technology. Was it for the lunar rover? So I'm also very interested in how the process of developing this electronics, because I imagine there's not a lot of oil and gas history that can be harnessed for a high temperature tool. So what kind of industries have you had to cross over with to create these tools?
Yeah, so kind of the interesting thing about that is, we talk about aerospace and like it's or combining with aerospace like it's something new. Teleco got started. It was a joint venture between Alpha Aquitaine and a company called Raymond Industries in Connecticut that was doing guided missile technology. So this whole MWD industry is a result of collaboration with aerospace, but aerospace missile technology, high shock, high vibration. But until recently, has not been high temperature. Apparently, these hypersonic missiles get hot, and that's why we're seeing some high temperature electronics development, I think. But we just stumbled upon the fact that JPL is putting a rover on Venus that has to go to 500 degrees Celsius, and so we had a great meeting with them, and very excited to work with us. We're just waiting to get this Space Act agreement signed. But at the end of the day, there's several things that brings to us. Some cooling technology, some packaging technology, and also the ability to manufacture some of these specialized components and circuit board compositions in low quantities. The challenge with oil and gas, if you want to make 20,000 tools, which seems like a lot to us, it's nothing to a chip manufacturer. They want 2 million. Yeah, there's a minimum order, right? And so it's very difficult to get somebody's attention for a lot of these things. So that's one of the other things that JPL brings to us, is the ability, and some of the other folks that we're speaking with, is the ability to manufacture in in oil and gas kind of quantities, dozens, hundreds, 1,000, 2,000 pieces, which you can't get major manufacturers to pay attention to.
Super interesting story, I would say, and I'm looking forward to perhaps telling this story when it's all said and done, like the how space exploration technology managed to work its way into geothermal. Okay, another question that is more specific to the tool. Is it possible for the tool to turn off, like during the connection of a drill pipe, just so it stops generating internal heat, or is that not significant?
It's a good question, but the tool is off. Especially when we move, right now we're battery powered. We're using high temperature batteries, but yeah, no, we power down electronics are powered down when we don't need them. Yeah.
Okay, how long do you anticipate the tool to be powered by the battery? Like, is it how long of a run can it do?
We have the goal is it's 200-hour battery life is what we're targeting. It's probably in excess of what we need, since most runs aren't that long. But everything is designed to go 200 to 200 hours. I think I'd be lying if I told you that 220 we have 220 Celsius, 225 Celsius batteries. And I don't think the battery life is 200 hours on that. I'd have to check, but the goal is to have the capability is to be 200 hours above 200 degrees Celsius. And with the turbine, we'll certainly have that.
Do you anticipate other applications of, say, the electronics and sensors that you're using? Like, are there other downhole tools that perhaps can become offshoots of what you do, of the tool that you're creating?
Yeah, there's as we get into this, and as everyone's learning, as we get into this, we're uncovering other opportunities for electronics. So production monitoring, tractors is one that's come up recently, where the off-the-shelf tractors right now, whether it's a wireline or a coil tubing tractor. Right now, the maximum rating on those is, I think it's 150 Celsius. And one of the challenges here is, if you've got a well that's producing and you need to go in and do something, remediation, there's no drilling rig on location. You're not cooling the fluid. You've got to be able to re-enter this well that's maybe producing at 350 degrees Celsius. And and these, as opposed to oil and gas wells, the return on investment on these wells is not 5 years. It's 25 years, 30 years. So these wells have to last for a long time. And we think that there's going to be a lot of reentry that's going to need to be done here to take care of what's gone wrong, whether it's flow rate, temperature, pressure. You're gonna have to re-enter these wells pretty regularly, we think. So that's where I think the big one is. But there's also obviously logging tools and things like that. We talked about geophones earlier. We just keep stumbling upon new applications for this. So yeah, I think outside of drilling, I think there's any place you need electronics in the oil and gas industry is the same thing here.
I mean, that's actually a very good point. Because if we reach the point where when we're drilling 300-degree wells, then you also need to have like workover tools or survey tools that function at 300 degrees.
Yeah, we don't have any right now. There's no production wells, right? So we haven't. I mean, nobody was doing this like 2 years ago, right? And that's the amazing thing to me. It's like, being a geologist, even when I was in school in the 70s, we talked about, okay, man, if we could harness the heat, we could go to Yellowstone and all the heat that's there, we could figure out a way to power the world. And here it is, 50 years later. And, I tell you, when I read the Fervo announcement that they were going to generate electricity from, essentially, we're generating electricity from granite, right? And so to me, it's amazing. It's like the Drake well in Pennsylvania. I just wish I was younger, because I think this is amazing. We're just right at the beginning of this, and it's going to be a heck of a ride. Really exciting times.
Okay, before we move on to my last question, there's a question from the audience that I think is quite interesting because two of them asked it. What is the temperature rating of the battery pack that you're designing for the tool? And does it also deteriorate with temperature?
Yeah, I don't know. The rating is 225 Celsius, and yeah, it's we decided to go with batteries because we think 225 Celsius batteries addresses the market in the short term. What the existing operators are drilling, they're keeping their circulating temperatures down below 200 degrees Celsius, 210 Celsius. So the need for the turbine generator, we kind of put that on hold. We put the development on hold because we had access to these batteries. But as we've gotten into it, there's some, high temperature batteries. They suck, right? I mean, it's just not. You run them one time. There's some safety issues associated with them. They're very expensive. So yeah, and yeah, the life is significantly deteriorated as you go to 225 Celsius batteries over the 180 or 185 Celsius batteries. Yeah, they're not great, and that's why we'll be testing our turbine generator here later in the year.
Okay then. Okay, so for the last question, I guess we'll just move on to actual projects and actual markets. So what are the more interesting projects you think can be deployable for your tool, and are there like new markets or new regions that you think can be opened up once we have a high temperature drilling tool?
Yes. So one of the interesting things is, John and I have been all around the world, drinking from the fire hose on geothermal here over the last 5 years. Every country we've been to is trying to do this. Every country, and every country. I mean, every country. And the challenge that we see is a couple of things. The main one is induced seismicity, and what Fervo's doing with hydraulic stimulation. But at the end of the day, it's fracking, and people figure that out, and there's a negative connotation associated with fracking. However, we're seeing some projects that are going to use fracking. There's one in the UK right now that's getting kicked off. We're starting to hear some discussion about this happening in Germany, and there's other places in the world that where that fracking is probably going to happen. But my view is that once Fervo starts generating electricity, putting a significant amount of electricity on the grid, that this is going to take off like wildfire because of the demand for the electricity. It's just there's no stopping it, and there's not really a lot of options. Now, the other part of it is closed loop. Whatever's doing, what SGS is doing, you don't have to frack. That's the advantage of it. So I would not be surprised if we saw more closed loop installations happening in Europe before we start to see EGS applications. And part of that is because you can use the hot water for district heating. And so even if you don't generate electricity, there's a good use for the hot water. But the other part of it is, as we said, hotter is better. And if one of the closed loop systems, you've got to push those down at the hot rock for those to be as efficient as to compete with natural gas on electricity generation. We've got to be able to push those wells down into 400 degrees Celsius rock. And in order to do that, you're going to need high temperature MWD and rotary steerable.
Okay then, and on that note, I think that was a very excellent webinar, and we're looking forward to you hitting that 300-degree threshold. Like that'd be a step evolution, I would say, for geothermal drilling.
It's common, man. I know it sounds crazy, and I think when we first started, and you've heard me tell the story, it's like for the first couple of years, when we're meeting with investors, they always have an advisor from one of the major service companies that told them it was impossible and you can't get above 200 degrees Celsius, and we tried it, blah blah blah. But with this approach that we have, I think we'll be at. I'm confident we'll be at 300 by 2030, which is now 4 years away, which is incredible. Yeah.
There's a bit of pressure, but then I would say that this industry has been all about doing impossible things through the past years.
Yeah, yeah, and I like to tell people in my career, look, we get oil out of shale for God's sake. When I was, my old boss of Superior Oil Company is rolling in his grave thinking about us, targeting shale. I mean, things change pretty quickly, and the impossible, it becomes a requirement here pretty quick in oil and gas. We've seen it, and same thing's happening here.
That's very true. Okay, then. Thank you, Steve, for that presentation. For everyone in the audience, this will be uploaded on our YouTube channel maybe in like a week. So just watch out for it. And then another 2 weeks, there's going to be another Focus on Geothermal webinar. So I hope you look forward to that as well. Thank you again, Steve. Everyone, I hope you have a good weekend.
Thank you.